So for this lesson, we're going to be taking another look at the idea of graphing trigonometric functions. But in this case, we are going to be focusing on graphing trigonometric functions using their key properties. In a previous lesson, we looked at graphing trig functions using transformations. In both of those lessons, you need to make use of the parent functions. And so it is a good idea, if you're not already familiar with, it is a good idea for you to become familiar enough with the parent functions for sine and cosine that you can recognize their shapes very easily. You know where the various functions start, and you can very quickly, either in your mind's eye or sketched out on a sheet of paper, you can see what simple transformations would do to these. So you can imagine what would happen if you reflected it or if you shifted it around a little bit. So we're going to be taking a look at what happens if I have a more complex set of transformations. One way you can still do this is you can treat this as a pure set of transformations. So if you have either sine or cosine written in what we think of as standard function notation, then you can read the values a, k, p, and q, and those give you access to the various vertical and horizontal transformations. Another very useful tool when you're looking at transformations of a function is if you know some of the points on the original or the parent function, which for sine and cosine, these are some of the things you need to become familiar with. These are available from the unit circle. Then you can transform those points using this sequence of transformations. And this sequence simply matches each of these parameters. So if I number those there, the first one is a vertical reflection and or a scaling, depending on the value of a, and that's basically a multiplication of the y value. So there's our first transformation. Then the k value is a horizontal reflection and scaling. Now the way that the k works, it's actually a division. So that's why we get the x divided by k. Then the p-value, which is the third one. Again, if you read them from left to right, this is the order in which you will encounter them. The p-value is going to give you a shift to the left or right, which is an addition or a subtraction. There's the third transformation. And then the final transformation is a vertical shift up or down. And so that would be the fourth transformation. This is a perfectly valid way to do it, but I do find it is a little bit more time consuming than looking at key features. So let's take a look at that in some more detail. The key features still match up to the A, K, P, and Q. We just use different terms to talk about them, and when you're visualizing, you might think of them a different way. So your A value, which is going to determine primarily your vertical scaling, so that's going to determine the amplitude of the function, which is the distance from the center of the curve, the axis of the curve, to the maximum, and it's the distance to the minimum. Your horizontal scaling, instead of thinking of that as a stretch or a compression, although please keep in mind, that is exactly that. It is a stretch, it is a compression, or it could be a reflection as well. These things are going to influence the period of your function. The horizontal shift left and right, it's still really, you know what, this one hasn't really changed. The only difference is we give it a different name. It's called the phase shift, and it tells you about the starting position of your graph. In my experience, this is the one that students grapple with the most, despite the fact that it seems maybe more straightforward than the others. For whatever reason, students find difficulty with this one. So pay particular attention to this as you're working through things and as I'm going through the examples in this lesson. And then finally, the vertical shift, the axis of the curve, which is running down the center line of your sinusoidal graph, can be shifted vertically, either up or down. This is critical. And this is actually where we start. We start with that axis of the curve. That's our first step. So we're going to start with a line to describe the new axis of the curve. We are then going to draw what I describe as an envelope for the amplitude. We're going to map out what's the new highest value and what's the new lowest value, and we're going to put lines there And that's our curve is going to bounce between those lines. Then we are going to take a look at the period. We're going to figure out what the period's going to be, and we're going to choose a scale that lets us represent both the parent function and the transformed function. Now, you won't always be required to include the parent function, so in which case you should only be thinking about the parent function fitting on your scale if it's a requirement. Sometimes you'll also be given the parent function, so a scale will be somewhat defined for you, and then you have to fit the transformed function onto that scale. Usually, but only usually you can choose a scale that is going to work out fairly nicely with whatever grid you have. But that won't always be the case. It can be quite difficult, particularly if the parent function is already present and the scale is defined. You can't always fit the transformed function into perfect sections. In that case, you have to do your best. You're going to have to estimate between grid squares. The phase shift determines where the starting point is for the graph. I'm going to take particular care when I talk about this in our example, so you'll see, or hopefully you'll see what it is that I mean. And then choosing your direction to draw is based on what we know about sine and cosine. The parent function for sine starts at the origin, and so if I just draw it there, how would we describe how it starts? It starts here, and then it moves up to the right. The parent function for cosine starts at a maximum. It looks something like that, but how would we describe the way that it starts? It starts going down to the right. If you have some vertical or horizontal reflections, they are going to have an impact on the way that your graph starts. Is it going to go, if it's starting up, then a vertical reflection means it starts down. If it's at a maximum, then a vertical reflection means it's at a minimum. This one started down from a maximum. If it's at a minimum, it has to start up. If you have a horizontal reflection, you can start here, but then instead of starting up to the right, you would start up to the left. If you had the cosine and a horizontal reflection, you would still start at a maximum, but instead of starting down to the right, you would start down to the left. So keep those things in mind. Speaking personally for me, I find that graphing by these key features is generally what I prefer. I find it quicker and easier to set things up this way, and I hope you'll agree. But if you don't agree, you can, of course, always use transformations. Okay, so the first thing I want to do, just as a side-by-side comparison, I want to determine transformations and key properties for this function. It's not trivial. I've put in every type of transformation, A, K, P, and Q. So let's start off with the transformations. So first of all, I've got my values here. So my A value, my K value, my P value, and my Q value. So reading this from left to right, the first transformation I see a negative sign. That tells me I have a vertical reflection. The next thing I come across is the number 2. That means I also have a vertical stretch by a factor of 2. Then I come across a K value of 3. And so a K value of 3 actually means I have a horizontal compression. So I have a horizontal compression by a factor of 3. Then I have x. Now normally this standard form is x minus p. So in this case the p value is actually equal to 30 degrees. And this would mean, that's 4, I'm going to have a horizontal shift to the right by 30 degrees. And then finally I have a q value of positive 1, and that is a vertical shift up by 1 unit. Another thing that I'll often do when I'm doing transformations, I'll actually think about, if I start with any point x, y, what are the various things that will happen here? So in this case, I've got a vertical reflection, so my y coordinate is going to change over to negative y. Now, these things actually can be incorporated into one. So rather than writing it all that way, I've got a vertical reflection and a vertical stretch by 2. So these two tell me that my y coordinate changes into a times y, but we actually know what a is. We know that a is -2. So how would I put that in there? And then a horizontal compression by 3. That means my x coordinate turns into an x coordinate divided by 3. A horizontal shift to the right by 30 degrees is going to take an x coordinate and it's going to shift it to the right by 30 degrees. And then a vertical shift up by 1 is going to take a y coordinate and it's going to change it into y plus 1 as it shifts up. Now, you have to apply these one at a time in order. If you were doing this as a full transformation, a single point being transformed entirely, then you would, normally we write the x coordinates first, so it would be, the first thing we would do is x divided by 3, and then we would add 30 degrees to that value. We would take the y value, multiply it by -2, and once that multiplication was done by order of operations, then we would add 1. So any point on the original graph of sine could be transformed this way. Okay, now let's look at key features. The first thing we're going to do for a key feature is we're going to draw the axis of the curve, and that's the q value. So the first thing I do here is my axis of the curve is now going to be along the line y equals whatever q is, and in that case it's y equals 1. My second choice is going to be an envelope for the amplitude. That's based on the a value. So the a value was -2. Now whether it's positive or negative, in case of the envelope, all that matters is the value of 2. So the amplitude of this is equal to 2. And so that means I'm going to have my envelope is going to be 2 above the axis of the curve. So that's going to be at y equals 3. And 2 below the axis of the curve, y equals -1. You don't normally write this part out. You might write out the axis of the curve part, but all we really needed from this was the amplitude of 2. I'm just trying to be very thorough here. My third step, determine the period and then choose a scale. Well, choosing a scale comes down to the graph. So what's my period going to be? The period, which I also use capital T to represent period, is 360 degrees divided by the k value, which in this case was 3. So that leaves me with a new period of 120 degrees. Step 4, use the phase shift to determine the starting point for the graph. So in this case, we are going to phase shift. And this is really the same as what we had before. It is right by 30 degrees. And then finally, so this is going to be our starting point, and then finally we talk about direction of drawing. Now this was a sine graph, which normally starts in the middle, or it starts on the axis of the curve and then goes up to the right. But this has been vertically reflected. So that means that our starting direction is on the axis of the curve because it's sine x. But now, because it is vertically reflected, it is going to be down to the right. Okay, and this part, the fact that it's going down here, that's because of the vertical reflection. So hopefully that's clear. Now, these things always become clearer, at least I hope they do, once we draw them. So let's move on to that now. So the first thing we get asked to do from our key features is draw the axis of the curve. The axis of the curve comes from the q value, which is at 1. So I'm going to go ahead. Well, first thing I have to do is I'm going to have to choose a vertical scale. Notice I don't even have to choose a horizontal scale yet. So I think I can go every other grid block. So that's 1, 2, 3, 4. And then down here is -1. Down the middle, of course, is 0. Let's put -2 on there as well. And let's go ahead and put a straight line at the Q value. So that's my axis of the curve. Okay, next step. You can see I've already done this at the value of 1. Draw an envelope for the amplitude. Well, that means my amplitude, so once again, so 2, 3, and 0, -1. So I need to now add another dotted line there. These dotted lines have no meaning other than as a reference, and a dotted line there. So now I know that my curve is going to exist between this upper dotted line and this lower dotted line. All right, so now period and scale. All right, now I just want to remind you, so our period, which I use the symbol capital T for, was 360 degrees divided by 3. And so that gives me a period of 120 degrees. Now notice I don't have the parent function on here. So I just need to fit this period onto this graph. So that would mean one full period would be 120 degrees, which means half of that would be 60 degrees. Half of that again would be 30 degrees. And then between those two would be 90 degrees. So this is enough room for me to graph with one full period. It is more challenging if the parent function is also present. Okay, now phase shift. This is the part where I've mentioned that students have difficulty. Normally, well, first of all, let's identify this. We have a phase shift, and as we discussed previously, it is right. It would help if I could spell right properly. Phase shift right by 30 degrees. So instead of starting on the y-axis, which is where the sine curve typically starts, my starting value or my starting point is going to be at 30 degrees. So my graph is going to start along that line. And in particular, sine starts in the middle, so I'm going to be starting right there. And I might cover this on a future slide, but I'm going to mention it here. Because of the vertical reflection, my sine curve is going to start going down to the right. Instead of going up to the right from the middle, it will be going down to the right because of that vertical reflection. So this is our starting point. Normally, the starting line, if you want to think of it like a race. The starting line, where all the runners line up, is normally along the y-axis, but now the starting line for this graph, think of it, it gets a head start in the race, so it gets to move 30 degrees forward in the race. And now we draw the curve itself, incorporating reflections. You can see that I've left I'm going to move this up just a little bit, hopefully to make it clearer. Let's see. Just to show, that's not great, but that arrow is pointing right here. So there's our starting point. And we know, well, what do we know? We know that after one full period, now be very careful here, one full period is 120 degrees from the starting point. So there is, and each 30-degree interval is 1, 2, 3, 4, 5, 6, 7, 8 squares. So with the scale that I've chosen here, and this is sometimes what happens, with the scale that I've chosen here, I'm actually going to end 1, 2, 3, 4, 5, 6, 7, 8. I actually have to extrapolate a little bit past the end, and that's one full period. That's where I'm going to end. Where's the middle of that going to be? Well, each of these 30-degree intervals is a quarter of a period because there were 4 of these in a full period. So I know I'm going to be back to 0 if I'm starting down to the right. Then after the first quarter, I'm going to be at a minimum, which is the bottom of my envelope. After the next quarter, or 30 degrees, I'm going to be back at the middle. And that makes sense. That's halfway between the beginning and the end. Then on the next quarter, I'm going to be at my maximum. And now I just do my best to draw a nice smooth curve. I'm going to let myself try that one more time. And over this way. And extending into that part where I had to go a little further. So looking back, I probably would have been better served if, rather than using 8 across for my scale, I could have chosen a tighter scale, particularly because I knew I had shifted over by 30, and then I would have been able to fit this point on my graph. Now, if I give you an evaluation, or if anyone else gives you an evaluation that requires you to do this, that's not your fault, especially if they've imposed a scale like this on you. But you really should be thinking about that yourself if you are drawing your own scale. Okay, so that's it for this lesson. Some homework to keep you busy.